Okay, hello everybody. So you probably know me after all this time. So I will talk about today about very high energy and ultra high energy gamma ray astronomy. And actually, it's a kind of field that is not really studied too much in Turkey. So basically, as I know, I am the only one. So I may try to mind trick some of you and drag into the field. Let's see if I can do. Okay, so basically, first, maybe it's good to start with gamma ray energy nomenclature, so the conventions. So basically, I mean, gamma ray covers a wide range in spectrum. So if you look some papers in that field, you will see that the ranges of gamma ray energies are defined in that way. So for the high energies, it's starting from 0.1 GeV up to 100 GeV, while for the very high energy part is from 0.1 TeV up to 100 TeV. And for the ultra high energy part, it's above 100 TeV or 0.1 PeV. You can ask why. I mean, this is because actually the corresponding instruments that are taking data in that interval, for example, for Fermi, is the working in that range. So they basically define high energy like Fermi gamma rays or something like this. Okay, so basically, actually, it was mentioned very nicely by Suat Hoca today and also Emre Hoca. There are two ways of detecting them, right? So basically, there's the satellite telescopes which operate in the orbit, and you can directly detect them. Directly means that gamma ray just hits on the detector on a satellite, and you whatever reconstruct energy and also the direction, whatever. But as long as you go to higher energy, it gets harder, right? Because actually you need larger volume detectors and large areas. So this is just whatever a few meters square, even not like this. So you need actually a very large detector. For this reason, you have to use something indirect, which is called actually Imaging Air Geranko telescope. So it uses Geranko technique, which I will dive into. And if you want to go higher energies, which is really I'm talking about the highest energy part of the electromagnetic spectrum, you need to go for water Cherenkov detectors, which I will talk. Well, I mean, it's mentioned several times, but there's some fact about the gamma ray source. So as long as actually you go to higher energies, like actually Pierre mentioned yesterday, I mean, the injection spectrum are coming from some sources, right? It's a power law index with -2. So it means that as long as you go to higher energy, the flux flows. So it's a natural thing that comes from the nature, right? And even this injection, so there are further effects. So, for example, whatever particles can diffuse in the galaxy and they lose energy from radiative losses, which Kai explained yesterday, like synchrotron, inverse constant. So it actually gets steeper, means that like maybe 3 or something. So it's another fact that actually there's a finite maximum particle energy, so nothing can accelerate particle until infinity. So it cuts at some point because of the power of the accelerator. Basically, as you go to higher energies, you will see less sources. So, for example, here's a sky map of the galactic plane taken with Fermi-Lab telescope above 1 GeV, and you can see actually a lot of point sources. Let's say also some extent one. And this is the one showing the same region, galactic plane above 25 TeV. You can see that there are less. Yeah. Okay, so why do we observe gamma rays, especially high energy gamma rays? So there's one thing actually Tolga mentioned today, that when you are dealing with X-ray data analysis, you start with maybe black body radiation and then add power law, whatever, right? But the point is, as long as you're at that high energies, like the EV energy range, there is no known temperatures that can actually generate these high energy gamma rays. For example, if you want to generate 1 TeV gamma ray, you would need like 10 to the 12, 10 to the 13 Kelvin temperatures, which we don't know that exist in the universe. So basically, when you observe gamma rays, you observe non-thermal universe, which means that they are just particles and their interactions. So no temperature, no black body, you can forget about all of this. And you basically trace them. So you trace their motion, interaction, whatever. And this is you can, whatever. Yeah, I come later. You will hear a lot. So let's keep it for later. But basically, it tells us where and how the most extreme energy particles are accelerated and also interact with each other. Right? That's the motivation. So basically, we said that particles. When you say particles, there are two family of particles that comes into mind, right? First one, electrons, so basically leptons in general, let's say. And the other one is proton or heavy nuclei, which you can say hadrons in general. And so these are interacting with something, which can be, for example, radiation fields. And from that, you will get probably inverse Compton scattering, which you can observe in gamma rays, the resulting spectrum. Second, that can be magnetic fields. The spaces, galaxies everywhere is filled with magnetic fields, which can result in synchrotron radiation, which you can still observe even from radio to gamma rays, like GeV energies, you can see that. Yeah. And the other one is the interaction with, for example, nuclei or hadrons with matter itself, right? The one known as Bremsstrahlung, which is quite good known, so I assume you know all. And the other one is the proton-proton interactions. This basically what's happening in the LHC, the collision of protons, which is a kind of resulting spectrum, especially in the gamma rays, right? So this is the general picture. So you can see the comparison of all these gamma ray emission mechanisms, the resulting spectrum. And so basically you see the synchrotron is coming from radio going up to near GeV. Then you Bremsstrahlung, which is actually less when compared to inverse Compton and neutral pion decay, which is the PP interactions actually. And basically, if you are dealing in the TeV and G and FO energy range, these are the two gamma ray production mechanism that you have to deal with. There's one point that you have to just take away message. It's quite hard to distinguish between them. You see, if you are measuring here, it's hard to know which one is which one. So inverse Compton scattering, actually Kai explained really nice. So it's just a recap to mention the important point. So basically, it's a electronic gamma ray emission mechanism. You basically have a kind of electron population which can be ultra relativistic, whatever, and you have low energy photons which are upscattered to the higher energies. And like I mentioned, it has a kind of boost factor, which is the square of the Lorentz factor. So just take simple, okay? So here's a kind of table which is done for the Lorentz factor of 10 to the 3, okay? So basically, if you have optical photons with that population, you can upscatter them up to gamma rays, which is quite good. And actually, it's just for 10 to the 3, and we know that for some pulsars, for example, for Krebs pulsar, it can go up to 10 to the 7, which means that you can even upscatter CMB photons, which is everywhere, right? Up to the gamma ray energies. Well, there's also another thing he mentioned, that actually that inverse Compton takes into place in two different regimes. Okay. One is Thomson regime, and the other one is Klein-Mishina regime. So what are the difference between them to understand? So in the Thomson regime, basically your photon, the incoming energy of the photon is way, way less than compared to the energy of the electron. While in Klein-Mishina, they are more or less same. So if you can think of this. In the Thomson regime, it's a very efficient gamma ray production mechanism. What does it mean to be efficient? Your energy, because your electron, imagine a single electron, can upscatter many, many, many photons until it cools down. So cool down means loses energy. But when you come to the Klein-Mishina regime, so they are more or less in the same. So maybe it can upscatter one or two photons, and then it cools down. So it loses the energy. So that's why you see a kind of cutoff there. For example, here how the connection between the electron spectrum index, coronal spectral index, and the produced gamma ray spectral index. Just for you, for example, take a number 2, put for the electron spectral index. Here, what you will get, you probably get. Okay, let's put 3, which is easier because in electron is a little bit hard, softer. So you will get 2, right? But if you put 3 here, you will get 4. So spectral index 4 means a very steep spectrum, which you read as like an observer. You will read as a kind of spectral cutoff. So let's see how the gamma rays are produced actually. In, for example, a pulsar environment. We heard a really, really nice talk yesterday from Benoit, which I really like actually. So he actually explained some magnetosphere and the pulsar region. So basically what we have here is a pulsar, right? And we have the magnetosphere, which is filled with electron, positron, plasma, right? And the plasma is actually co-rotating with the neutron star. So they are rotating in the same way. Up to where? Up to a kind of threshold we define here, which is the light cylinder, right? Okay, everything is fine here. And this is the magnetosphere region. So what happens here? Actually, you have some open magnetic field lines, which probably you can't see, but they are going like this. And light cylinder is actually defined, the last point at the closed magnetic field. And here, you know, electrons, positrons, they like following the magnetic fields. So basically, they go out like this. So it's an outflow, a kind of, let's say more scientifically, ultra relativistic cold magnetized plasma outflow, which is going like this. This region is called pulsar wind. Okay, and here cold means actually it's not thermalized motion, so it's called like they are going like soldiers. Okay, so not thermalized, and it's ultra relativistic. As I said, it can go 10 to the 3, 10 to the 7 Lorentz factor, and it goes up to where? It goes up to a point which is called pulsar with termination shock. This is basically the momentum flux carried here is balanced by the ambient medium. So it then creates a kind of structure which we call pulsar wind nebula. Okay. So, so what is the difference here? Here actually all the structure is rotating, like somehow, and you can, for example, have gamma ray here due to synchrotron or curvature radiation. But as an observer, you will see a kind of pulsing gamma ray emission, which makes your pulsar a gamma ray pulsar. Okay, but the difference here, it is stable. So here is exactly the part where the inverse Compton takes place, and it can upscatter because here actually, it's now ultra relativistic hot magnetized plasma, which means that if you look at the individual particles, they are still ultra relativistic. But if you look at the population, it's thermalized. Everything is thermalized. So okay, yeah, we talked that. Okay, yeah, there's something new that I'd like to mention. Actually, really recently, like I think last year, something like this, very high energy gamma ray emission, which is pulsed, is detected by from a pulsar called VHE, and it's up to 20 TeV. The problem is that from either synchrotron or curvature, you cannot get to that high energy. Okay, you can go to GeV energies, it's fine, but you can't go to TeV energies. So they say, okay, we need a kind of region here inside the current sheet, which is that wobbling-like structure that actually upscatters photons to these energies. And they said that, okay, there can be some magnetic connection lines there, so magnetic connection regions, which can further accelerate electrons, whatever there, and they can upscatter the photons in that region, so we can see kind of past very high energy gamma ray emission. Okay, I mean, story goes too long, but yeah, I will stop here. Yes. This one, it's a very complicated structure, like actually Ena showed yesterday. So, okay, there is a kind of region here, which is called separatics, that actually the last open line somehow connects just a little bit beyond the light cylinder. And imagine, there's not you see it as a kind of photo, but actually all the structure rotates, right? So it kind of creates a kind of wobbling current sheet. So, yeah, this is exactly the thing. No, it's not addition. It's an outflow, ultra relativistic, cold magnetized electrons, positrons, whatever. Okay, so let's see it in an example, in a real example. So this is the nebula, which was shown in Chandra. It's really nice. But if you look at the TV, well, it's not so interesting, but it's just like this. But it is interesting and spectral. So here you can see the really multi-wavelength spectral energy distribution of the nebula. Okay, so even starting from radio, yeah, whatever, infrared, ultraviolet, and I don't know, and there are some X-ray, whatever, gamma rays, ultra, very high energy, ultra high gamma rays energy, and you can actually make a SED in multi-wavelength. You can make a multi-wavelength picture. So what you see is here is a huge peak, which is actually a synchrotron peak that we talk. And here a second peak rises, which is actually inverse Compton peak. So We are zooming here in that picture. Yeah, you can see that actually this is the model that actually you can model it and you can get the gamma ray emission expected from synchrotron, which really fits quite nice. And the rising inverse Compton here. So maybe the takeaway message here, if you are, for example, just looking at Fermi-Lat data, you will see that funny structure, right? Which is going down and going up. So actually it tells, these are called spectral features or signatures, and it tells you something that basically some kind of physical interesting process takes action there. For example, one emission mechanism just dies away and the other one is just rises. Okay. So you would like to try, for example, not power law or exponential cutoff power law, or maybe a broken power law, which is just a combination of two power laws. So second one, as I said, it was a hadronic interaction. It's proton-proton interaction. And it's basically a collision of protons. Okay. So in that interaction in particle physics, but you know that there are three channels which are more or less equal branching ratios, right? So like 33%, whatever. So basically after that, a subsequent, so proton-proton interactions followed by the subsequent pi-zero descent. So the natural pion directly descends into two gamma rays, and this is the gamma rays that you are looking for, okay, from PP interactions. While on the other hand, you also have the charge pions, and like actually, Shortage mentioned today, they descend into neon and neon neutrino, and you may want to go further, and then the neons descend into electron and electron neutrons, whatever. But so where it happens in general, so you have somewhere cosmic ray source, like it can be a supernova remnant, whatever it comes to. It's not important right now, and it goes and that's actually injected cosmic rays goes and interact with kind of molecular clouds somewhere, which is the target material for you, and then you will see gamma rays and a simultaneous neutrino emission. That's important because this is the only way you can distinguish between actually neutral pion and inverse Compton if you are just looking at the gamma rays, so no multivariate. So here it becomes the what? It becomes a multi-messenger. So the robust way to identify the origin of a source to be hadronic is to look for actually neutrinos, which will come actually later in a more detailed way. Yeah, I will explain it in the later talk in Pevatrons because it's more related, but just a quick takeaway message. So if you have the energy ratio between the gamma ray to protons are generally like canonically assumed to be 10%, which means that if you have 1 PV protons hitting to some target, they will produce 100 TeV gamma rays. For the neutrinos, it's like the 5%, so the same protons will produce 50 TeV neutrinos. Okay. Yeah, the story is getting more interesting as long as actually you go to higher energies. But there's a kind of fact that we know, which is called photon interaction at the same time. So basically, it's your photons are somehow colliding each other, and they produce an electron-positron pair that you lose your information. So let's talk on that plot, okay? So we have the energy range of nearly all electromagnetic spectrum, and on y-axis you have distance and some indicators, okay? So like the galactic center, nearest galaxy, whatever. You can see, imagine that it's a vast empty space, so you don't have any baryonic matter, whatever, in between. Just space and the photons are traveling, okay? So up to now, everything fine. And when you go into a spectrally gamma ray region, then this process takes place, okay? So you can see the Feynman diagram here. But basically, if you are dealing with extragalactic astronomy, so which is outside our galaxy, then the effects start to see around 100 GeV. So exactly in the very high energy range, it starts. So if it's some Z source you observe, you will see the spectrum to be diluted, yeah? So for example, here is a good example of a gamma ray burst spectrum, okay? So this part is what is actual data taken, okay? And they had to correct it to get the intrinsic gamma ray spectrum of this. And yes, for ultra high energies, it's not really well starting at that point, but it's for high energies above 200 TeV, 300 TeV, you can see the same effect for the galactic astronomy. And I will explain it more later. but it's just to have an idea. Okay. So up to now, we have some idea about what are the gamma rays and how they are produced, whatever. And now we come to the part that the detection of them. And I'm lucky that Suatoji actually explained a lot of this, so I may skip some part. So this is the Cherenkov radiation, which is it's just emitted when the charged particle is moving faster than light in that specific medium, right? And it creates, like exactly he said, it's a shock-like structure that you see. It's a very particular emission, which you can see is the charged particle, and it has that opening angle, okay, which you can see the formula here is inversely proportional to the n, which is the refracting index of the medium, and the other one is the beta velocity of the particle, whatever. And basically, you can have that angle depending on, for example, and that for the air it's very small, like 1.4 degree, but if it's the water, then it will be larger. Okay. So, okay, and one point which is important, like he explained actually, so what happens here that it actually polarizes environment when the charged particle goes, and then particle leaves, they just go back to their ground level, so they emit radiation, but it's a destructive here in that case, but here they make a constructive, so you see a net light, okay? And this means that Cherenkov radiation only happens in a medium. So you can't have a Cherenkov radiation in the space, okay? Good. And okay, there's the kind of formula which is called Frank-Tamm formula, and it describes the spectral density of Cherenkov photons, and you can see it's like 1 over lambda square. So which means that you go to higher frequencies, higher energies, the intensity increases, okay? That's one of the key factors, and which means that when we look at it, we will see a glowing thing in bluish color. Like here, for example, here is a change of a reactor fuel, so which is surrounded by water, heavy water, something for protection, and you have really ultra-acidic particles entering here because of the decay of the fuel, and they glow. Okay? They create Cherenkov radiation. So this is what if you plot, it will look like this. But another thing, like actually, Suatoji told today, you need to detect them, right? So you want to make astronomy, starting point is to detect them. And you will need to use some PMTs, photomultiplier tubes. And you can see, for example, for different photomultiplier tubes, the quantum efficiency plot of this, depending on the wavelength, okay? So if you want to make astronomy, good one, you would like this peak to have closer to the here. So you will get more photons, yeah? That's the idea. Okay. Yes, extended air showers. Actually, okay, we consider two cases, okay? And actually, Suatoji explained the one, which for the cosmic ray, so I'm happy about it. It's basically a cosmic ray coming and hitting to a kind of whatever atom molecule in the atmosphere. And this is exactly PP interaction that we see. So it creates muons, whatever, and they descend to, first it produces pions, then they descend to muons, and actually all the muon things are coming from the background, coming from the atmosphere. But let's focus on what happens if a gamma ray, a very high energy gamma ray, say 1 TeV photon, enters in the atmosphere. Okay. So it actually comes here and it just passes by in the vicinity of a kind of whatever nuclei that exists in the atmosphere. Okay. And because of this, it has a kind of, the pair production effect. So it basically turns into a positron and electron pair. Yeah, that's what it creates. So the energy threshold is around 1 MeV for this process, and you have 1 TeV photon, so life is easy for it, okay? And then there's also another step taken. So you basically have electrons and positrons, which are ultra-relativistic in that medium, which is atmosphere. So basically they radiate Cherenkov emission. Okay, and sure, and you have that relativistic electrons, which are again passing by in the vicinity of some molecules, which then creates a Bremsstrahlung, which is it produces again a gamma ray, and the gamma ray goes again to electron-positron pair, whatever. It goes like this, and it creates a kind of electromagnetic shower. The point is, first interaction is pair production. What happens here? And it develops. Okay? And we have electrons, positrons, and photons inside. So basically, I mean, Earth is continuously bombarded with these kind of structures, and well, you have the ratio. If you want to know about the ratio between how many gamma rays, very high energy gamma rays, or hadrons come, is like 1 to 1, 1 to 1,000, 1 over 1,000. So you have to distinguish these two, which is the key problem. Yeah. Okay. Oops, I will skip that one. It's just how to model that shower basically, and because you would need it. But yeah, you basically imagine that there's a kind of splitting length, and the particle are losing half of its energy, and then by using it, you can just estimate the maximum shower size, so how many particles in it, whatever, and the shower depth. Yeah. So this is used actually in kind of simulation programs. Like Corsica or whatever, because in the end, for the energy estimation, you would need it. Okay. So what happens? I actually brought a torch here, but it doesn't work. Sorry, but let's try. Okay. So okay, gamma ray enters the atmosphere, and it creates the electromagnetic shower, right? Like we talked. So there are actually a lot of ultra-relativistic particles inside it that can actually create Cherenkov radiation. And we said that its opening angle is around 0.1 degree. And this process actually occurs around like 10 kilometer, 10 to 20 kilometer, whatever, high altitude. So basically, if you make a small trigonometry here, you will find out that it actually creates a kind of Cherenkov light pool on the ground, which is around 120-meter radius. So you can put a telescope there, a Cherenkov telescope, which is optimized for the Cherenkov light, like I showed you, and there is a dish of the telescope, and there are mirrors on it. You can reflect this Cherenkov light to a kind of camera, which is composed of PMTs, photomultiplier tips, right? Then you basically record the image of the Cherenkov light, which is on the ground, actually on a camera. You just reflect it, right? So there are some things that Cherenkov light is actually super fast, like 10 nanoseconds, something like this. So you need to really take a picture of the sky like billion times in a second, right? So you need super fast electrons. It's super dim. So you totally need a kind of total darkness to observe this light. Total darkness means the time that the moon is not present in the night. Okay, so it's total darkness. And basically, so you will see that it's like a ellipse. This is called Hillas ellipse. And it actually really includes three different important things. First, it tells you about the direction of the incoming particle. Wow, interesting. It tells you about the energy of the incoming particle, and it tells you whether it's a proton or just a kind of very high energy gamma rays. Well, I mean, you can imagine that, for example, well, I will try. It doesn't work, but okay. So this is actually what you see, right? So it's like the Cherenkov. So it says opening angle. So you'll see this is the Cherenkov pool on the ground. And you can do like this, actually. So for example, it's coming like this. And you can take the major axis and you can make a kind of plane perpendicular to it. And you will be sure that the particle is the incoming particle is in that direction. Second, actually, you can just sum the total amount of the photoelectrons here, and it's proportional to the energy of the incoming gamma ray, right? So we said more energy, it actually creates more splitting lengths, more particle, and consequently, you have more detected photons. Yeah. Well, you can do actually stereoscopic system, which means that you actually observe the same Cherenkov light with several telescopes, and then actually you can have a quite good angular resolution, which is around 0.1. So here you can see what I mean. Okay, and the third point is the gamma hadron separation. So as I said, you have to understand which is a proton, which is a kind of gamma ray energy, and sure, the cosmic ray showers, they are much more irregular. So the Cherenkov light emitted from that and recorded in your camera, it will be super like irregular like this. So you can basically parameterize that ellipse, like the width and the length, whatever, and then you can compare. So for example, you can see that this is the width of the ellipse that you see here, for example, like the width and the length. And you can see that for the gammas, they are quite nice peaked at some region, right? And for the protons, well, maybe length is more or less same, but the width is still wide. So you can use it. It's totally a machine learning classification. For example, like TBAE boosted decision tree or something like this was done for this. It's like the random forest. You can think like this. Okay. Okay, energy reconstruction. I will skip it. So here, basically, this is one of the operating system, which is called high energy stereoscopic system, HES. It's just referring to Victor Hess, actually, you saw in the beginning on Suat just told. And here you can see, for example, a 5 telescope, which are like separated like 120 meters. And there's a huge one in the middle. Okay, this is located in Namibia in the southern hemisphere. So you can nicely see the galactic plane above it. Okay. So these are 4 telescopes that there's a huge one in the middle. So you can say that, oh yeah, maybe catching for higher energy gamma rays, but no, it's totally on the other way around. Because actually, for a lower energy gamma rays, there are actually less Cherenkov photon produced, right? Because your energy is less, they can produce. So in order to collect more photons, you would need a bigger dish, bigger mirrors. So let's take an example for it. For example, this is a quite known supernova remnant called RX J1713, whatever goes like this. And this is a sky map of this excess map of this object taken with the HESS telescope. Okay. By the way, I put sometimes some paper names here, so you can go like here and check whatever in general. Okay, so well, in the end, what you have in the at hand. So, for example, for this source, you have like 164 hours of observation spanning like for a long time, and you have gamma ray events, right? So, for example, you have say that whatever 30,000 gamma ray events above 250 GeV, for example. So you can distribute them. You also have the direction information because you just reconstruct the kind of direction in radix coming from somewhere in the sky. So you can just go and fill a 2D histogram and you will have the map. Well, you can also cut on energy, say that, no, I just want to take the events above 2 TeV. Then it changed. Then you started to make morphology, energy-dependent morphology analysis or something like this that you can see actually subtle differences between them. Well, you can make the spectrum of source, like actually Tolgozha is quite similar. And even you can go and combine it with, for example, other observatories like Fermi-Lat gamma ray. So here, this is the spectrum obtained by HESS observation, which is like here. And you can also combine it with the Fermi-Lat gamma ray data together, and you can a broader spectrum. So it tells you more somehow. But still, if you want to make a kind of go and try to understand whether it's hadronic or leptonic, well, both model, that's the red one is the electrons, the inverse Compton. Blue one is the protons, that's the PP, proton-proton interaction. Well, they look like same, so you can't really conclude anything. And in the end, it's not only one emission mechanism, right? In that kind of object, you will see probably some part is leptonic, some part is hadronic, something else. So this is the data analysis methods. It's also optional, but well, I would say that if you would like to dive into that field a little bit, there's a kind of really nice gamma ray astronomy package called Gamma Pi, which has quite nice tutorials in it. So you can go and look at that page that you will understand. If asked, I can understand this. Otherwise, it's a little bit optional. Yeah. So this is the survey. That these are actually a kind of survey. Yeah, you can also point and observe the sources, but you can also scan the galactic plane, for example, and try to search for new sources. And these are the results. So you can see the flux of the whole galaxy. This is the galactic center, and you can see that actually there are many sources. How many sources? I mean, actually, at that time, it was a 2018 paper, and it was a detection of like 78 very high energy sources. And some of them are, I mean, not associated, so it's like dark sources. You don't see any other counterparts at other wavelengths. Okay? And well, we can, so nice to see the galactic plane up to about I mean, one TV up to like 50 TV or something, right? Okay, so up to now we talked about the imaging atmospheric Cherenkov technique, which I explained it, right? But there's another way to do the same astronomy, okay? Because we talk about that the electromagnetic shower or the whatever hadronic showers there. You basically go higher in a kind of whatever plateaus at high altitudes, and you can put a kind of water tanks there, and you will force particles like electrons, muons, whatever, to emit Cherenkov emission in that tanks. So it's the same. And you can, because they are cheaper, so you don't need like camera, electronics, whatever like you have here, and you can distribute it in a quite very wide ranges. And it actually acts like a super big camera, while each of that Cherenkov tank is a photomultiplier tube. Right? So basically, you can do this astronomy by using, and this is called water Cherenkov technique. And okay, so one of the example actually you heard yesterday is the LASO, Large High Alt Air Shower Observatory, and it's a kind of actually hybrid observatory, which has actually many different types of detectors. You have electromagnetic particle detectors, neon detectors, Cherenkov detector array, like I explained, and well, you can still make astronomy with this. So what is the, if we compare, what's the advantages and disadvantages? Well, for the Cherenkov telescopes, actually energy range is 100 TV. This is the maximum. Yeah, somehow you can actually expand it to maybe 300 in the next generation, but this you have limits. Okay. And but for the particle accelerators, because actually you have a wider, like the effective area that actually Suat told, you have a wider area of detection area because your array is much more larger. So you can actually detect higher energy photons. Okay. And sure, and this is duty cycle. So you basically, as I said, you can only for Cherenkov telescope, you can only observe in a part of a night. Okay, but these are, since you are forced them to emit Cherenkov in water tanks, they can fully operate day, night. It doesn't matter. Okay, so it's continuous. And the field of view, these are small, so you basically observe a part of the sky, while these are quite large, so it actually detects and observes whatever goes above. Okay, and for the energy resolution, yeah, we have Cherenkov telescope much better with respect to that, because actually, and also angular resolution, because we have actually more telescope here, but it's like acting a big, huge, whatever camera. Yeah. Okay, so I am about to finish, I think, my talk. Okay, I'm good actually. And so, yeah, there are some observatories, for example. So we have the Veritas in Arizona here in the United States. We have MAGIC in La Palma in Spain. So these are imaging atmospheric Cherenkov telescope, like I mentioned for the HESS one. HESS is located in Namibia, and LASO is here in China. So we have Tibet Air Shower Array, which is a similar thing here, and we have Hawk that we will hopefully hear from Fidin in next lecture. So she will actually focus on these ones rather than that. Okay, so for the future, so there's the Cherenkov Telescope Array CTA project that I also worked in for more than actual 10 years. And it's a kind of next generation imaging atmospheric telescope. So next generation means that, so currently what we see here, we have like 4 telescope, 2 telescope, 5 telescope, whatever. The point is to increase sensitivity. Yeah, so you have to make a jump in science, because up to now, like in 20 years, we learned a lot of things about how to do this astronomy. Now we can go further, build more telescopes, because we know what to do. Okay. So in this way, it's like around building around 80 and more maybe telescopes, and it will be 10 times more sensitive than the current generation atmospheric telescope. There will be 2, one in northern hemisphere, one in southern hemisphere. So the difference is that, I mean, if you are observing from ground, if you want to make a galactic science, that you would probably like to go to the southern hemisphere because the galactic plane goes like this. Well, in the northern hemisphere, you can still make it, but it's more like maybe extragalactic astronomy. So if you want to observe Crab Nebula, it's better to go to northern. Okay. Okay, and this will actually extend the energy range up to 300 TeV, like I said. And it will be done basically by the combination of three different telescopes. So that life-size telescope is actually similar to what you see in the middle of the HESS telescope. And this is the middle telescope, which are actually the four telescopes around. And there will be small size telescopes, so you can actually make it very wide and cover a very large area. So that will actually increase hopefully your sensitivity and the energy range. This is for the high energies. Okay? So this is the comparison of instrument sensitivities. That's important. So you know the sensitivity curve, but just to remember, so you have a kind of curve given here, and if your source or spectrum, whatever is above, you can detect it. If it's below, you can forget about it. Okay. So as long as you pull them lower, it means it's the better sensitivity. So for example, for the HESS, currently it's somewhere like this, and CT8 will make a jump like a tenfold in sensitivity. Okay. And so this is the idea about what improvement sensitivity means. Okay. So basically, currently we are like here, and there are some even maybe hidden sources that we can't see because of the sensitivity constraints we have. Right. So when you improve the sensitivity, so this is this real data I showed you. Okay. And this is what CTA will see probably in the future in the galactic plane. So going up to maybe 500 source detection. And well, I mean, it's not, there are many things that actually you can study. I mean, even the dark matter, whatever. I work in that part, pelotrons, and we will talk about it. So you will be able to sleep more, hopefully. Okay, and so thank you very much. I hope it was nice.